Hello, everyone. Good afternoon, and welcome to yet another asset session here. We are lucky to have a very distinguished Mr. Shreyas Srinivas here to speak on models, and most models are query models. Thanks to Professor Harsh Prahlad, he is being invited to give a lecture here. About the speaker, I'll give a brief introduction to him. Shreyas Srinivas is a final year PhD student at the CISPA Helmholtz Center for Information Security. Is advised by Professor Christoph Renzen, currently at Reykjavik University. His work spans distributed clock synchronization, ASIC design for clocking in VLSI systems, and formalization in Lean. He was a maintainer of the equatorial theories project, and with his co-authors refuted the conjecture that EFX allocations always exist for monotone valuation functions in discrete pair division. His current research focuses on integrating interactive theorem proofs into theoretical computer science. He is here to talk on most models are query models. Over to Shreyas. Please continue.
Hi, thank you for the wonderful introduction. So I'm Shreyas. I'm a PhD student at CISPA. And basically, as the introduction said, I'm based in Germany and I'm doing my final year of my PhD and I'm neck deep in lean formalization. That's basically my current focus. So before we get into the talk itself, some meta stuff. So this is an extended version of a talk I gave at the Max Planck Institute for Informatics, specifically to the algorithms theory group. And much of the content is focused on the formalization of algorithms and complexity. And I'm aware that the audience is much broader. So I'll try to keep it a talk that's of wider interest. But I apologize if there's too much lean code or something like that. And if you don't understand it, it's fine. I'm just trying to give you some broad idea of what's happening in this world. The work that I'm doing is this work that I'm talking about is basically largely work in progress, and I'm also trying to get you to contribute to it. So, without further ado, this talk is broadly about this notion of formal mathematical proofs. Now, mathematical proofs are already formal objects, but a formal mathematical proof is a proof that can be checked by a computer. So you write something in a computer language, and the computer checks it for you. In particular, we are focusing on this interactive theorem proof lean, which has been in the news of late. And my goal is to build libraries of formal proofs for theoretical CS. So we'll go over what all of these things mean in a moment. So we'll have a number of these digressions where we take a shallow dive into some concepts. So the first one is, what is an ITP, an interactive theorem prover? Roughly, it's a piece of software. In principle, you give it a theorem statement and a formal proof, and then it tells you, well, indeed, this formal proof is correct, or this formal proof does not prove this theorem. And usually the thing that's checking the proof against the theorem statement is called a kernel, and it's generally written to be as a small piece of software you can verify and trust. The reality is ITBs are a little bit more complicated. This is to facilitate ease of use for humans. So the kernel is usually a very small part of an ITP. And normally when you give a theorem statement and a formal proof, the ITP will return something that describes the state of a proof, such as the hypothesis and what goals remain to be proven. So let's take a lean example to understand this, and I will go over this example in some detail. So I have defined here a piece of lean code. There's a definition called sum list, which takes a list of natural numbers and returns the sum of the elements of this list.
Shreyas,
Yeah.
a quick question. Can you go to the previous slide? So how is this different from just a formal proof checker? What is the usual formal proof checker? We don't have the word interactive in front of it. So is there some back and forth going on between the left box and the right box to indicate
Yes.
the interaction? Or is it just because the formal proof, in a formal proof system, you do have the same thing. You have a theorem statement, a formal proof, and you write it in Frege, you write it in something, and it just checks and tells you if it's correct. So how is this different from that? And yeah.
So this I'm about to explain in the example.
Okay.
Okay. So here I've taken a screenshot of a piece of lean code. So there are two panels, as you see. On the left-hand side, I have a definition, def sum list, and a theorem about sum list append. On the right-hand side, I have placed, my cursor is not visible, but can you see my mouse pointer right now? I have placed my cursor here. And Lean is actively telling me that at this particular point in my Lean code, this is the state of my proof. As I scroll through this Lean code, and as I add more proof steps, this proof state will get constantly updated. So that is the interactive part of Lean. Prahlad, does that answer your question? Prahlad, I can't hear you. I can see. I can't hear you.
Can you repeat what you said? The last year.
Okay, so there are two panels in this snippet you see, right? There's a left-hand side where I've written some code, and there's some right-hand side where it's saying case cons, and it's giving me a list of variables with their types. And at the end, you have this turnstile symbol with what is basically the goal that you need to prove. This part of the theorem prover is basically interactively updated. So as you move your cursor through the proof, you get different proof states. As you add lines to your proof, you get this proof state updated. This is the part where you interact with the theorem prover. And on the right, and you can actually do much more, but let's focus on this example for now. So sum list basically sums up a list of natural numbers. It is defined in a...
Just to understand it again, so this sort of this example which you're displaying, there's a left panel and a right panel, and as you go through the left panel, line by line, the right panel keeps changing, at least in the Lean. This one
when I'm in the Lean editor, yes. This is a screenshot.
When you are in the Lean editor, and it
gives
you the progress, and this is the interaction you're talking about.
Yes.
Okay.
Okay. So sum list is basically summing natural numbers. And if you are familiar with some Haskell or OCaml programming from some computer programming course you took, this is essentially a recursive definition. A list can be an empty list, or it can be an element, a natural number, prepended to an existing list. This double colon operator says prepend x to xs. It's just standard notation. And the recursive definition is simple. It just says you add this element to the sum of the rest of the list. The theorem is just an illustration. It says if I sum list the concatenation of two lists, that is the same as summing the two lists separately and adding the sums together. This is until the equal to symbol, you have basically the theorem statement. Now, Lean provides you a sort of convenient set of automation tactics that corresponds in some way to what you mathematically write. So here we use the induction tactic. We say we induct on XS, the first list, with two cases. In the first case, XS is empty, that is nil, and then some simplification steps are applied, and we show that indeed sum list of XS is 0, so 0 plus sum list of YS is YS. And we also simplify the appending. So basically, this is a trivial case. The second case is the so-called cons case. So I just told you that we prepend elements to an existing list to produce a new list, and this in functional programming lingo is called cons. So we cons X and XS, and along with that, Lean gives us an inductive hypothesis, IH. So when I took the screenshot, I placed my cursor after this arrow. This is where I'm going to prove the induction step. So Lean showed me an info view with a goal, which said case cons. As you see, this matches the arm. And there's the list YS, the number X, and then XS. And then there's the inductive hypothesis, which just says that if I sum list XS and YS concatenated, then that's the same as sum list XS plus sum list YS. Then at this point, I'm sure you can see that I'm just proving the result of the inductive step. And since I completed the proof, if I also got goal.accomplished on this line. So this theorem, which is in line 7, has been proved. So I get a goals accomplished. So this is what interacting with Lean looks like. There are other provers, and there are even other forms of interaction. So Agda famously has a very different style of interacting with the proof checker, and is more famous among people who work on foundations of mathematics. Higher order logic is a system of logic, and on top of this, there are two theorem provers, Isabelle and Hall 4, which is used in a lot of cryptography. Rock, also formerly known as Coq, is a theorem prover which is similar in foundations to Lean and is widely used in the programming languages world. And there are also other historical theorem provers which are not in active use today. Automath was like the first theorem prover from the 70s. New PRL was run from Cornell in the 90s. And Mizar came from the other side of the Iron Curtain from Poland in the 70s and was quite active until the 2000s. So this is Lean does not live in an isolated world. It has a lot of history behind it, and learned a lot of lessons from these provers. So now we go into a second digression. Why are we formalizing mathematical proofs? Fortunately for me, Patrick Massett, a mathematician from the University of Paris-Saclay, wrote a wonderful paper in 2021. So the QR code leads you to this paper. Feel free to bookmark it. And he gave 5 specific reasons for formalizing. And we're going to go over them one by one. So the first reason he gave is checking. So what does checking mean? Well, you take an existing proof in the literature, you encode its definitions, and you check that the proof is actually correct. And if you ask a person, well, why do you use interactive theorem provers? The most likely answer they'll give you is to check proofs. But you can also use them to check the output of symbolic and neural net AI. So that expands your tool set as a mathematician to do things. So the thing is, if you ask Patrick about this point of checking, he'll say, well, it's not the most important use case of theorem provers. And the other 4 points are far more important. The second point is exposition. So if you take a typical mathematical paper, which is in like mathematics or TCS or physics, you have a paper written for a specific audience. And if you do not come from this subset of a tiny subset of people this paper is aimed at, understanding it is hard because there are lots of hidden assumptions, unclear definitions, and so on. So a formal theorem prover can clarify these assumptions by letting you interact with the code as you go and understand what's happening. A closely related use is teaching. So think about your normal assignment setup. You have a weekly assignment with your mathematical course, TCS course, and then you have the tutor who reads whatever you've written, and then you get feedback once a week. Now imagine the same thing happening on an instantaneous basis. You have one of these real analysis proofs, you have these epsilon deltas, and you don't know whether you're applying them correctly, but Lean can now tell you immediately, well, this is your proof state after you do this. This is your proof state after you do that. And in fact, a lot of people are using Lean for teaching. In particular, real analysis is being taught with Lean in Rutgers, and proof theory and such things are being taught by Emily Real. And there are many other such courses. Another use case is collaboration. And I mean collaboration beyond the physical whiteboard. So if you're a theorist or a mathematician, you sit around whiteboard with your colleagues, and then you write some stuff on the whiteboard. And once you all reach agreement, you write a paper after several rounds of iteration. Now, I believe I'm going to show you an example that says that you can actually collaborate on a much wider scale. Finally, creating mathematics. This is an ambitious claim, but let's say you are doing some mathematical work and you're kind of stuck and you want to check whether you're making progress and you're doing the right things. You can use Lean to check it. You can take a Lean definition, tweak some parameters, and see what changes this creates in all your theorems and proofs. And by virtue of the difficulty of formalizing, you're forced to create better abstractions that remove all the irrelevant details. So this is actually a fairly important use of interactive theorem proving that's only recently started happening more often. So I'll give you some examples of all these points. So this is a physics example.
Shreyas, one more question. So the previous slide, you talked about exposition. So writing theorems in a formal system, and hopefully that will help for better exposition. But we do this in math also. You are supposed to write proofs in ZFC. But if somebody writes proofs in ZFC, I'm not going to understand it at all. Somehow the English write-up seems to help me better to understand the proof. Why does Lean offer you a better... So is this... What do you mean by exposition over here? Why would something be written in... I agree, it has to be formally written, done and stuff. But why does formal writing offer better exposition?
There are two answers to this question. The first answer is, as I said, well, you may think, well, okay, I'm formalizing something in ZFC, and then you may give it to another person, and they may read just your top level theorems and then step through your Lean code, and the Lean will show them a proof state, which will give them a better idea of what your proof steps are doing. That's answer number one. Answer number two is to be found in the programming languages literature, where standard formalization has become the norm for the last 15 years. So if you look at a typical paper in this area, you get all the formal proofs separately in Roc. And the paper itself writes much shorter, more intuitive proof sketches. In contrast, if you take a stock paper, they do write intuitive proof sketches, but they are littered with a lot of extraneous details which need to be explained so that the reviewer is convinced that the proof is correct, which interferes with just explaining the intuition, right? Prahlad, I can't hear you
Yeah.
again.
Can you hear me now?
Yeah.
I follow your second example of formal languages, programming languages, where this is essential. But the math community has also caught up to it. For example, when the polynomial Freeman-Ruzha theorem was proved last year or a little recently, they not only proved it, but they also wrote it up in Lean to check this. How did the writing in Lean help in any way in any of these bullet points? Or was that just show that it can be written? What was the purpose of that?
So actually, initially they wanted to formalize it for the sake of formalization, but it turned out a few things happened in the process. So firstly, they formalized it before submitting the paper for review. This paper was, therefore, when the reviewer sees this paper, they already know this is formally checked. So that's something the reviewer does not have to check. The second thing is they actually, so if you look at the conjecture, it's a claim about the size of adding two subsets of a group and how the number expands. And there's an exponent in this, which was conjectured to be 11. And what happened was, the exposition was so clear that somebody thought, hey, let's change the exponent to 10 and see what breaks. And let's change the exponent to 9 and see what breaks. This clarity of this exposition made it possible to ask these kinds of questions and then check what's happening and then improve the bound to 9, which was the last time I checked it. Again, I can't hear you.
Thanks. There's a lag in the mic. Yeah.
Okay. Anyway, so I want to give some examples of these points, not all of them, but recently in physics, there was a preprint by Joseph Tooby Smith, who was the head of the physics formalization effort, or one of the leading members of this effort. And they, in this paper, he formalized an old result of the so-called Higgs doublet model potential. And in doing so, found a very critical bug in this paper. And what would the thing is, physics formalization is actually far behind mathematics formalization. As you know, in many parts of physics, a lot of concepts are not even fully formally stated in pen and paper. So given this starting point, it was fairly impressive that they found something, an error in a series result. So that shows that there is utility to the checking side of formalization as well. So for collaboration, I picked a project that I was a part of, the Equational Theories project, which Terence Tao launched at the end of 2024. So this in turn was inspired by another project.
I have a question, Shreyas.
Yeah.
Hi, I'm Arkadev. So this physics thing, did it bother the physicists at all?
So I'm not a physicist, so I really cannot tell you.
Okay.
But I know that the person who formalized it was a physicist. No, so he was bothered.
But the larger physics community, did it sit back and look at it, or it was like besides the point?
I believe it was. I believe there was some attention from the physics community, but since I don't come from that community, I have to take the word of the physicists whom I know, and among them, it was fairly well received.
Okay. Fair.
Okay. So I wanted to. So yeah. So we're talking about collaboration. So back in 2024, Terence Tao had the following question, and it was actually inspired by a prior project, which I might mention in a moment. And the question was, well, now that we have a theorem prover, which can serve as a base of trust, instead of collaborating around a whiteboard, among people we know very well, can we just collaborate on a global scale, where people can just create an online account and contribute to mathematics? So Terence Tao started the Equational Theories project in September 2024. And from the beginning, I was one of the maintainers of this project. And the goal was, you take this structure from universal algebra called a magma. It is the most basic algebraic structure that exists. You have a single set and a single binary operation. And as such, there are no rules imposed on this operation. So then you start adding one equational law, one equation that applies to this magma. And then you start asking the following question: is this equational theory equivalent, or does it imply another equational theory or not? If it implies another equational theory, you should be able to use equational rewriting to reach this other theory, this other law. If you cannot do this, then you should produce a counter example which says, here's a set and a binary operation. And here's here's the set satisfying this equation, but not that equation. And this was motivated by a Stack Overflow question from years ago. But when we started this project, we started with 4,694 equations of up to 4 variables. This was generated by a Python program. And then we set about solving them systematically. And a lot of collaborators joined in. And at the peak of this project, there were 50 plus collaborators. Eventually, there were 34 authors on the paper. So given 4,694 equations, there are 22 million pairs of equations. And now you have to reduce this to some 10,000 equations through symmetry so that you can feasibly do something. And once we did this, the positive implications were solved very rapidly in a few days to a few weeks. I think by 1 month, we were done with all of them. And the anti-implications, which were much more challenging, took another 5 months. And in the process, we employed a lot of old-fashioned automated theorem provers like Vampire and Provenine. And we discovered that these are actually incredibly powerful tools. In contrast, at that time, LLMs were not so good. But the key point here is we could collaborate on this scale on the internet. And we could do citizen mathematics. So the last example, in the last case, I want to present 2 examples. The first one is actually a class of examples. If you want more details on this, I recommend visiting the Erdos Problems webpage, which is run by this mathematician, Thomas Bloom, and has been the source of a lot of AI plus maths news in recent times. Basically, if you go to this web page, you will find a list of problems which have been solved, problems which are believed to be open. And every day, somebody takes an LLM and some lean and mixes both of them to reach a solution of some or the other problem. And at this point, I've lost track of how many problems have been solved at this rate. There's something every day. But the other one that I was involved in was using good old-fashioned AI, where we were using actually 2 interactive theorem provers, Lean and Isabel, because there were 2 different people working on this. And we refuted the EFX conjecture, which was this conjecture from econ and computation, which said that given a valuation function that's monotone and for each of a number of agents, you can have a certain kind of fair allocation of goods, which meets a certain fairness criterion. So there is a lot of reason to believe that interactive theorem provers can expand what you do with mathematics as well. So why are we discussing formal proofs in this day, and why not 20 years ago? 20 years ago, formalization was in a very primitive state. Today, we have unified mathematical libraries such as mathlib and ROC's MathComp. Formalization itself has gotten much faster. So 2 decades ago, Francois Gontier and his group formalized the odd order theorem in ROC, and it took them several years to do this. And as Prahlad just mentioned, the polynomial Freeman-Ruscha project was formalized fairly quickly in 3 weeks. So that's a frontier result getting formalized in basically no time. And the last reason is unfortunately AI. If you've been paying attention to arXiv, there's been a huge increase in the number of preprints, and last year's talk and licks have received a substantially large number of submissions. So I think formalization can help us sort out through this flood of new papers and such. So why did I mention unified libraries? So I'm giving you some IT buzzwords now. You would probably find them on LinkedIn, but I use them with good reason. Let's say you write a paper and you formalize it with Claude, and then I write a paper and I formalize it with Claude, and we are both talking about circuits for some reason. But if both of us come up with different definitions, then the reviewer has to check each paper from scratch and try to figure out if we are proving the same theorems and same lemmas and so on, and whether these 2 things are even compatible. With unified and common definitions, we have one trusted baseline to start with. We don't have to reinvent the wheel every single time. And if we can reuse them, then we can prove more complicated things. And the seamless interrupt thing is, again, an engineering buzzword, but I introduced it because I want to emphasize that when you start using interactive theorem provers, mathematics becomes engineering, for better or for worse. So some examples of unified libraries, there's mathlib. It has approximately 2 billion lines of mathematics. It started in 2017 and has grown hugely since then. There's the 2 recently started community libraries, PhysLib and CSLib. These are unified physics and CS libraries, and it's still early days, so we don't know how they're going to turn out. And there are also a bunch of downstream libraries, including my algolean. Yael Dillis is AdCombi, which is for additive combinatorics, and the cryptographic protocols library, VCVIO. So the people are also developing these downstream libraries so that they can make progress on certain problem domains faster than the central libraries allow them to. There are also other libraries in ROC and AGDA and Isabel. They all, these theorem provers have slightly different foundations, and that enables them to, for example, write mathematics and homotopy type theory, which is this foundation Voivodsky got a Fields Medal for. So the takeaway is that we've reached a point in formalization where we don't need to reinvent wheels. So my goal is, my focus is on formalizing algorithms and complexity. So this is where we start getting into TCS. I hope I can keep your interest from this point. So basically, I want to build a unified library of algorithms and complexity in Lean. And this means I want to be able to formalize textbook results, but also reach frontier results fairly quickly. And I want to make use of Lean's math library so that I don't keep reinventing standard math proofs. And know that there are already some formalized algorithms and other theorem provers, and there's also this functional programming algorithms that have been proved, but none of them reach this ambition of having a unified library using MATLAB and such. And the goal of reaching frontier results is fairly non-trivial. You have a gazillion computational models. You have 80 plus years of papers, most of which were written with a very small audience in mind. And there was no Bourbaki style unification of theoretical CS like there was in mathematics, which has greatly helped MATLAB. And further, if you go to recent literature in the last 20 years, if you take Spielmann and Teng's Laplacian solvers or the recent Maxlow result, these are huge papers and they skip over a lot of tedious implementation details. And if you want to formalize all this in that level of detail, maybe you'll finish this library in the next century, right? And by that time, you'll have more results. So then the key question is, how should we formalize algorithms? Know that when I say use the word algorithms here, I don't just mean the stuff you run on your computer, but also circuits, interactive proof systems, and whatnot. All of these words are covered in the notion of algorithms. So there seem to be two extreme possibilities. One is, well, you just take a Lean function and you try to assign some complexity to it. And on the other extreme, you write detailed machine models for each of these gazillion machine models that you have in computer science. And both of these are, in some sense, not the right option. Let me explain why. So I think all of you would agree, as mathematicians of one sort or another, at least, I believe most of the audience is mathematical. So if I give the same input to two functions and they always produce the same output for any input, then those two functions are equal, right? If you can nod, I'll know I've heard your question. No? Okay. So this property is called functional extensionality. There's this notion in type theory of extensional versus intentional equality. And what we mathematicians call equal functions are extensionally equal functions. But this is a problem. Because in Lean, and actually this is a MATLAB theorem, merge sort and list sort are two functions which are sorting lists. They have the same input-output relationship, which means merge sort is the same as insertion sort. And that's going to create problems. So if I have a proof of a claim that the time complexity of merge sort is O of n log n, by a simple rewrite, I get that the time complexity of insertion sort is n log n, which is obviously absurd. The point is, a Lean function, by virtue of being extensionally equal, does not carry all the structured information that you have when you write an algorithm, right? Let's look at the other option. Now, when you start formalizing fixed machines, you run into the problem of which machine you want to formalize. And let's say you want to pick the RAM model. I've already listed some models here, but take the moral RAM model, let's call it that. What is this for moral RAM model? It's actually 10 different models hiding under the guise of one model. So are you going to formalize all of them? That's a lot of work to do. Then once you formalize this model, you take a modern paper, say the Maxlow paper from Rasmus King et al. In 22, and you have this 80-page monster paper with a huge list of things that you have to implement, most of which are not even relevant to the argument the paper is making. And that's just a simple fact of modern algorithms. We don't need to write that level of detail. There's a combinatorial argument here, right? And that's the key thing we are trying to prove. We are not trying to prove all the prior work correct. We are not trying to implement and prove the implementation correct. We are proving something combinatorial. This is mathematics. So the idea is, well, a fixed machine model might feel like the correct approach as a computer scientist morally, but it is too far removed from the abstraction we actually work in. So we are back to square one. We have two extremes. We can't just use lean functions, and implementing machine models is going to take forever. And indeed, one of the goals of CSLib is to formalize one such model and assign it one such time complexity and cost function and space cost function. And that's good, but then you're ignoring the other 100,000 models, which you would still like to formalize and for which there's still a lot of stock and fox literature and soda literature, right? So this is why I bring in my model, the so-called query combinator model. And the library in which I built this is called AlgoLead. So before I go into what this model is, I want to mention that this is a model that people keep coming to from different angles over the past several decades, from cryptography, from distributed systems, from Oracle complexity of various models and so on. So this is an idea that keeps getting reinvented, and everybody realizes then that, oh, well, somebody else has already done this in some other domain. So what I call the query combinator model is basically a unification of all these efforts into one model. I actually discovered half of the literature in this area only after implementing this model. And I was able to, I realized that I could actually, combine it all inside this. And the library itself is called AlgoLean. So this is a pun. It could be read as algo plus lean, algorithms and lean, or it can be read as algol plus een, as in like something like algol, which is a very famous programming language that has inspired a lot of theoretical computer science pseudocode. So the query combinator model describes algorithm models and algorithms. Yeah.
One more question before you go into AlgoLean. So I just want to know, in the CS community, so in the math community, there was the polynomial Freeman-Ruja project. And you also mentioned something happened in the physics community. There's been project. Has there been a large enough project or a large enough sort of CS statement that has been verified? I know several individual folks have written proofs, formalized CS things, but has it been a large enough thing which has been verified by the community at large? Has been any such instances, or?
Unfortunately, okay. So there is one example.
There has been a cryptographic protocol that is used in practice. Has it been written down and verified the correctness of the protocol?
So actually, cryptography is one of the few areas where this has been done extensively. So there is a system called EasyCrypt, and it is maintained and it was created by Gilles Barth, and this group is based in MPI Tübingen, security and privacy. And in this particular domain, and then there's another prover called Tamarin, which is a state-based prover, which is maintained by Cas Kremer's group. So this is an area where this notion of proof is very well explored. There's the Dole protocols, and there's provers based on that. There is the EasyCrypt and Jasmine system. And they have formally proved things, even post-quantum cryptographic protocols like Kyber. So this is one of the few areas where this concept
they
is
have
well
done
developed.
it, but they used lean to do it? That was actually that's what I'm.
No, they haven't used lean.
So the two other examples I gave were lean examples. The polynomial and Ruja. In cryptography, of course, you prove security. It's important to do it, but my question is: the success of lean, has lean been successful in doing any CS theory projects?
So actually, yes. Are you aware of the ecosystem around zero knowledge library proofs?
Yes.
So there's been extensive success in lean, and one of the libraries I mentioned, VCVIO, has been used to verify cryptographic protocols in lean. And this is used in many of these cryptocurrencies like Ethereum and derivatives of Ethereum. So, but there's also, I would say, recent success in the distributed systems world, where a system called Veil came out in 2024, and this was followed by a system called Loom as its successor. And this comes from NUS Singapore. And what they did is they embedded a distributed systems prover called Ivy into Lean. And the nice thing about this was that they could call these automated IV style tools and TLA style tools. But when the proof failed in these fully automated settings, they could revert to a lean style proof with mathlib. So this was a way of combining automated and manual verification in a convenient way in one single setting. This area is called multimodal verification, and in this lean has been very successful.
Okay, thank you.
Okay, so we are going to talk about the query combinator model here. So the idea, it consists of three pieces. I call the first piece queries, but essentially they are the basic operations. Now, if you take a RAM model, there are the basic arithmetic operations. In Turing machine, there's a single step transition of a Turing machine. In circuits, there is the evaluation of a single circuit node, and so on. These are basic operations. But in principle, a basic operation can also be an abstract procedure that you don't want to verify, something in the literature, something like a max flow procedure, and you want to say, well, I assume that I have this max flow procedure. I assume I have an oracle calling this procedure and giving me the response. I don't care about how this oracle is implemented. So the concept of queries is basically asking an oracle to do something, and that oracle can be a RAM machine model or something more sophisticated. It could also be an explicit oracle in the interactive proof sense or online model sense. And then a model of this query is just going to describe formally what the query does. So whatever data structures you need to execute this query, everything goes into this model. As a person using the query to write programs, you never see the model. You only see it when you use them to prove theorems about the program. The models specify what the queries do and cost. And then there's the combinators, which describe how the queries are combined. Now, the word combinator might sound mysterious, but it's just your for loop, while loop, conditional statement, recursion, procedure calls, any way in which you combine these queries. So that's seems simple, right? Like that's basically how you describe any algorithmic model. Like go to a first year undergrad class and this is what they teach you. But they teach this to you in a very abstract moral sense, right? Not in the formal sense. So what does this formally mean? Like how do you implement it? So in Lean, a query type is fairly straightforward. I specify a query type is just a function type. It just says, well, I have a query and it's going to give me an output in some type. And so I have to provide this type to the query in advance. The model is also fairly simple, right? The model takes a query type as parameter, and it also takes a cost. There are some details I'm hiding here, but essentially the cost need not be a natural number. It could be a pair of natural numbers. It could be a more complex structure that we haven't even thought of yet. But it just needs to be a commutative monoid, which is in some sense where you can add things and you have a zero and and the two operations, the things that I said a model should do are covered by these two fields. There's the eval query, which returns the value that of this particular type, iota, and the cost, which returns a cost of this query. But then the question is, like, how do you get the combinators? And for a while, it was commonly believed that there was only one safe way to formalize algorithms, at least among a subset of the community, which was that you write a custom language inside Lean. So Lean lets you describe an abstract syntax tree and specify some nice syntax for it. So this would be a domain-specific language. Essentially, you would specify ways to implement conditional statements, loops, variables, substitution of variables, recursive calls. You would write a general framework of proofs of termination, and then you would somehow say, well, given any algorithm, I have a Lean function that computes what this algorithm computes. This, if you've read the PL literature, is a lot of work. This takes several years of implementation. And what do you get in return? Well, you get complete control over all the operations your language can perform. You can basically, there's no way to sneak in anything that the language does not allow. This is called, this is one of the, okay, there are several criteria for what a deeply embedded domain-specific language is, and this would qualify as such a language. The second option is, well, Lean already implements all these things for us, so why not reuse them? So I'm going to introduce a bunch of terms here, and I will explain what these terms mean in a minute. But the nice thing is Lean actually implements everything that I mentioned, and there's a thing called a monad, and Lean provides special syntax for writing programs in monads, which looks a lot like your imperative algol-style pseudocode, right? So yeah, our model is essentially going to use something from CSLib called free monads. And we'll get down to what that is in the next digression. which starts here. So I'm going to give you the functional programmer's view of what a monad is. The concept comes from mathematics. The concept has been around since the 60s or 70s. But we want to start with some more basic problem. So there's a class of languages called functional programming languages. Lean itself is one such language. And unlike C or C++ or Java, what you write in Lean are pure functions. So if I read a function like, given a function with the argument x, return 2 times x, I expect that no matter how many times you call this function on 4, I always get 8. I don't get 9 when you take some input. I don't get 10 when you did some network operations and all that. This is like a mathematician's version of a function, right? Like you fix the input, you get the same output every single time. But programming languages are actually interacting with the real world. You need to have some way of interacting with the real world. You need to take inputs, and your inputs could change how your program behaves. You need to interact with other computers. You need to write to files. So how do these how do we model these real world effects in programs? So there's a bunch of effects that I've mentioned, but this is not the only kind, right? So around the 1990s, there was an oversimplified answer. No, I'm oversimplifying it, but somebody, there was this person called Mogi from the category theory world and functional programming world. He proposed the use of this category theoretic construct called monads. And the TLDR is you attach some sort of bookkeeping to your pure functions. And the bookkeeping becomes part of your input-output relationship somehow. So instead of producing values like the previous doubling function did previously, you produce the values and the bookkeeping. And you can do this in a compositional way. You don't have to reinvent this bookkeeping every single time you write a bookkeeping function. So this standard pattern is in the Haskell and functional programming world called a monad. This is basically all you need to know about monads. So concretely, a monad must be is a kind of, let's say, an environment where you have two kinds of operations to combine programs. So instead of, you take a pure value and do a no operation. You do nothing. There's no bookkeeping to do, and you just return it. So the cost of this pure operation, if at all you assigned it something, would always be 0. That is, you take a value of type x, say, and produce a do-nothing program that will return x, right? And the second operation is the more complex one, the bind operation. And this bind operation is going to take a program that produces a value A. It's going to take another function that takes a value A and produces another program B, which means there's some bookkeeping and the value of type B. And then it's going to produce another program of type B, which composes the bookkeepings of these programs along with the values. So you get the values from A to B, but you also carry over the bookkeeping. So this is generally what we call monad. And the very high level idea, and there's a lot of implementation detail and scripting, is to use bookkeeping to keep track of these costs. A free monad is basically a version of a monad that is free in the algebraic sense. You take the weakest possible equality relation you can apply on them, and you say that this is a monad. And usually this corresponds to an abstract syntax tree of the monadic operations. So this is what you see here, and when I write this inductive free M. It has this constructor, 2 data constructors, pure and lift bind, which is very similar to bind. And what you do using these things is build a set of operations. So you have this lift bind, which has an operation, and the rest of a program, the continuation. And you continue to build it as a tree, and then you do something with this program. Okay, so this idea is actually from goes back to 2008 in Haskell, and has been used in several domains: hardware, some basic graphical user interface languages, and so on. And also recently in verifying cryptography. So this happened in Lean, by the way. And in the EasyCrypt world, which is specifically designed for a certain subset of algorithms on a very limited sort, some basic algorithms on linked lists were modeled with this idea. So why do we care about all these monads? So apart from the fact that we want to do some cost bookkeeping, you get this nice familiar syntax that looks now a lot less like Haskell and a lot more like C++. Yeah, Prahlad, you have a question.
Yeah, so you've gone to abstraction as a monad. A monad is a very generic, this one. Can't this be done with something like a class or a structure an easier this one. That is, there is a sort. The problem is there's a sort function and there's a sort algorithm. You want to distinguish between these two things. That's the issue. For the sort function, you're not going to be able to distinguish merge sort from insertion sort. But a sort algorithm, possibly, there are different types of sort algorithms which come with this. Can't you come up with a, or is it because Lean is a functional language, you can't do these classes?
No, you can do these classes. In fact, the class that you, if the class that you would invent if you were to do this would be a writer monad. You would add a function that
a
keeps
far
track of.
more general object than what is needed. That was my question. Yeah.
Okay, so monad is, can do several things. One of them is keep track of logs. And if you were to implement this structure that you described, this class you just described, that would end up being a writer monad. And once you declare it as a monad, you can use all this fancy syntax and theorem proving facilities. But more importantly, why am I going for a free monad? Okay, so if I write a writer monad for one program, like let's say I'm doing merge sort, and I write this in this writer monad, then tomorrow you might write another program which tracks a different set of operations, and then you end up mixing them up together, and you actually don't know what model you're using anymore after a while if you continue doing this. I want to explicitly specify that these are the basic operations I'm counting, and the consequences for the complexity of the algorithm come from the costs of these basic operations. What a free monad does for me here is it says it takes this query type and produces the weakest possible monad from this type. So now I have not one model, but a family of models parameterized by this model type, the query type.
Okay.
So there's some niceties with using a monad. So there's a nice familiar imperative style syntax. So now you feel like you're writing Java or C++ code rather than Haskell. And there's also there's a fancy way of proving properties of such theorems. I haven't actually proved this theorem because I borrowed this directly from the Lean language reference. So this is a code from there to show you that there is monadic verification condition generator, which lets you prove things in the way you would prove it in paper using preconditions, invariants, and postconditions. This is the familiar world of algorithms that we start with in undergrad. And my claim is that I can use this for everything from algorithms and sequential setting to circuits to quantum circuits and so on. Anyway, that's the end of the digression. So now we actually have all the pieces we need. So we have the query type, we have the models, and from CSLib, and thanks to the nice implementation of my co-author on this project, Tana Du, we also have free monads. So at this point, if you have any questions, I think I should take them. Otherwise, I will. Any questions so far?
I think there's no questions. You can continue.
Okay. So how do you go from evaluating queries to evaluating programs? Fortunately, monads come with nice machinery for that. So I lift the program monad into the identity monad. And then what I do is I lift for timing the program, I lift it into a time monad, which is basically a writer monad. So this is basically telling me, well, use the time query function and then tell me what the time is. So I've saved myself a lot of pain with writing recursive definitions and some very basic lemmas that I will use repeatedly by using free monads and everything that it provides me. So, and then the other thing is now I can start writing programs in C-like language. So we have now reached a point where we have a trade-off. On the one hand, on the one extreme, we had this Lean function which had no useful information. On the other hand, we had this one fixed machine model which you have to implement every algorithm, and we seem to have reached a midpoint where we can just specify the operations we care about and use pure for everything else. And there you can use even axiom of choice if there's an operation that you don't care about in terms of complexity. So at this point, I'm going to go into some simple examples. This would be a good point to ask questions about this sweet spot. None? Okay, I'll continue. So the first model example I have is a comparison model. So I deliberately have two queries in this model. One is a compare operation that takes two values of a given type alpha and returns a Boolean. The other is an insert operation, which inserts an element alpha into a list alpha. Because for very artificial reasons, I want to compute the number of times I insert an element into a list. Then I define this sort model. This is the model part, right? And then I take a function, a Boolean function. And now that I have access to this Boolean function, I can, well, just interpret these operations. But when I write a program, I do not have access to this Boolean function. So I have to use the comparison operation on this type. I do not even know that this type is ordered at this point. There's no way I can tell that this is a type that might have some order. So I've parameterized it with a type for which I do not know an order, and I'm forced to use this comparison operation. So I'm writing the ordered insert function. This is a program in the sort ops insert head query model, and it returns a list. And I like functional programming, so I really like writing things in this recursive style. So I just match the pattern match on L, and there's the empty list case, and there's the case where the list is a cons of an element and list. And is there anybody who has any difficulty following this function at this point? I can read it out if you'd like, but if not, then I'd go further and show you what proofs of correctness and complexity look like. Prahlad, do you have questions? Okay. So there are two theorems. One is a correctness theorem and one is a complexity theorem. So the insert odd eval theorem lemma says, well, if I take an X and a list and I have this comparison function, then the time the correctness operation is proved by saying that this insert odd is equal to mathlib's ordered insert, which is a pure mean function. So I don't actually actively prove the correctness theorem here because mathlib has a proof of correctness of the pure functional version. I just say that this my function, my program evaluates to the same function. This is a nice use of functional extensionality in that sense. So functional extensionality is not all that bad. Anyway, the second theorem is the complexity bound. It says, given a list S, L, and an element X, and this comparison function, when I evaluate this program on X and L, the time under this model is at most two parameters, L.length and L.length plus 1. So I actually define an order on this cost structure of number of inserts and number of compares. So the order is basically if component-wise order. It's also partial order. So this is an example of a complex cost structure. So you might ask me, well, isn't that cheating? Well, yeah, because I'm basically inventing this weird model, and I'm saying, well, my complexity is something in this weird model. So, well, this is not really a cheating per se, because I have a notion of reductions here. And in principle, if you take a basic model like the RAM model or the Turing machine model, this is also a query model. So I can reduce my programs to this lower level model if you want me to prove that it actually works in models you're familiar with. So you can reduce the custom query models to basic models. This means you're kind of free to use your literature model. And once you have models, you can compose them. So for example, how do you produce randomized versions of each model? You don't have to invent a random model for every case. You just say, well, I define a random sampling model, and I define a cost for this model, which is fairly trivial. And I take the distribution from the PMF monad. And then I take an arbitrary query and I randomize this query, which means I give it the ability to make random samples on the type alpha. And this is done by taking what we call in Lean a sum type. So now you can define the model for this composed query by just taking the two possible values of a sum type, the left side and the right side. If the left side, you evaluate the query with the model that you already have. If it's the right side, you use the random queries model. And the same goes for the cost. So now you actually have a cost function, a cost type that's going to be the cost of the random query or the cost of the original query that you took as parameter. So another example, I have a few more examples. I think I'm running out of time. So I'll show you some 3 more examples very quickly. So now I've shown you that you can write programs, and I've shown you that you can write cost structures. So what other models have I encoded so far? I've encoded AC circuits. That's a constant classical unbounded Fanon circuits. So you have the nice thing about these circuits is they actually, if you look at them as such, they look like formulas. They look like trees. But it turns out that you would just have to carefully account for the sub-circuits and match this identical sub-circuits, and you can also get the circuit size out of this system. So, and in addition to this, so the inductive type of circuits look like this, and naturally we can write programs on it. I'm not going to go over the writing of programs again, but if you want to ask me questions about that, it's fine. But we can also do quantum circuits. So this was written by my collaborator Tanadu again. He wrote a set of operations which correspond to standard gates in I think okay, I forget the name of the person, but I think they got Clifford gates or something. So there are basically these standard gates: Hadamard gate, Pauli gate, C0, and there's also finally an oracle gate, which is an arbitrary quantum oracle, and they all return these unitary vector, these operations, unitary operations on vectors. So we can reuse the circuit metric that we already used for circuits, because that's the same cost function. You have the same depth, the size, formula size, circuit size, and everything. And lastly, I have the Robertson-Webb query model. So this is explicitly defined in the literature as a query model. So what you're doing here is solving the so-called cake cutting problem. But your cake is actually like this unit interval. And therefore, you're given two queries. I give you an interval of this cake, and then I ask you, well, how much do you value this cake for each agent? And this model can respond to this query. So for an agent I, and the extremities of this interval x and y, eval will tell me, well, what is the value of the interval, closed interval x comma y for agent I? Mark is also often called, I think, move or something like that. But what it says is, if I'm agent I, and I start at the point x in this interval, and I give you a value, how far do I have to take a knife and move it to the right until I reach point y, such that the unit of that interval is this value? So this is a fairly standard model to handle all of these cake cutting problems in continuous fair division. And this is explicitly defined as a query model. And note that the return type is sometimes a real number. And recall that it is actually impossible to compute on real numbers. You can't even say two real numbers computably decide the two real numbers are equal. Nevertheless, Lean lets you write non-computable functions as mathematical objects. And because we have this monadic structure, we can count how many times we call these queries. So to recap, I think at this point I should conclude. Why did we build this meta model? What did we get out of all this? And where is this going? So the good news in this model is that it's lightweight. We don't have to reinvent a programming language, and I don't have to write 2 purple papers to get some meaningful progress. It allows us to reuse everything that's already a Lean operation. But for me, the most important thing is it identifies this layer of abstraction between what we write in a stock or soda paper and what is actually implementable by saying, well, here's the combinatorial content of what you're doing. So if you want to formalize last year's shortest paths paper, you say, well, I assume for the moment that there's Dijkstra's algorithm query, and there's a Bellman-Ford query, and a query type for Fibonacci heaps, and I build this composite model. Then I prove the results of this paper from last year. And later I can implement these queries as their own programs in the lower level model. So that's how you get to frontier results very quickly. And lastly, it also lets us reason about models explicitly. So you can write reductions between models. So this also means, for example, if you have Turing machines, which we already have, we can define a complexity class P and NP on these Turing machines. But then we can go one step further. We can define reductions from an arbitrary model to a Turing machine. We can put a predicate on it that says that this reduction is polynomial time in the Turing machine, which means we can define a model agnostic version of P, NP, and all the other complexity classes. And in fact, we also have at this point definitions of BQP, and soon we'll have BPP as well. So it's a lot of algorithms in complexity theory immediately drops out of this meta framework. So I think at this point I will stop. And this is a QR code to my library. If you have any questions, I'm happy to take them now. But if you want to see some appendix slides, I'm also happy to do that. So I stop here.
kind things. Open for questions. Just wait for the mic. Do you have any?
I have a question, Shreyas, Prahlad again. So there's a general thing of trying to use lean to write formalize stuff in theoretical computer science, math, and also theoretical physics and stuff. We talked about the specific issues that were there in theoretical computer science. Basically, this notion of an algorithm, a model. These are stateful things, unlike math things, which are functions, which are pure functions. TCS theoretical physics, we talk little more closer to the real world. So they are stateful objects, and there's a problem in trying to capture this fully formally. There's an issue, and you suggested this monad approach, or which then further the query approach. What have the successes been? Using this, have you been able to capture some nice CS theorem or a physics theorem in this language? Or it is still in its early stages where we are formalizing how things to be done. We are setting up the stage.
So I think the biggest challenge has been to find a unified framework in the first place. Now, this is one of those ideas that looks obvious in hindsight, but doesn't actually pop out immediately. So especially because, okay, you want to have a structural way of computing complexity. You want to specify your unit cost upfront, and then you want to build complexity on top of that. So this library is at this point, I think, less than 2 months old. I think I started it at around early April, roughly around the time you reached out to me. So yeah, we haven't actually gotten that far yet, but I believe that already this library lets us prove things like Hastad's lemma that you're working on, and maybe even time and space hierarchy theorems. That should be a doable thing in the near future. And for frontier results, I think, as I pointed out, you can start proving frontier results up to the literature, what I call the literature oracle. You take the pieces of the literature you use and treat them as oracles, and then you prove the core theorems of your paper, and then you can postpone the proof of the literature results to a later date. It sort of allows us to do this top down.
Hi, thanks, and also to maybe further elaborate on the question of Prahlad and also what Arkadev asked earlier. I know that a paper appeared on Archive last month called formalization of QFT, and the authors of the paper are well-known people in string theory and mathematical physics from MIT. So these are like people who are very well. So I do know that this has achieved attention from very serious physicists, and not just the one which the speaker knows.
Thanks. I'm aware of this formalization, but I also recall that this was heavily AI generated, and they've been forced to do a lot of work to make this work well with FISLib. So it has this property of being it looks wonderful in the beginning, but there's still a lot of work to be done on that.
Actually, another question, especially in today's world in which people are vibe coding like crazy, very easy to sort of vibe code and say you got a lean formalization of something. There's tons of AI slop being generated across. In fact, okay, just yesterday, I think there's a group, Atlas, that announced that they formalized like 30 odd undergraduate textbooks or courses in theoretical computer science out. Now, how does one, possibly they are all correct and they've done a good job, but how does, I'm almost sure they use vibe coding or agentic models to come up with these lean formalizations. How does one even know that what they have there is right?
You don't. You don't, because a proof checker can only check a proof against a given set of definitions and theorems. So if
how do you know that the definition that they have written or the theorem that they have written is actually the theorem that I care about?
You have to read it and understand it. There's no alternative to that. I mean, you could use an AI to help you summarize it. It could, explain the code to you, but ultimately, you need human review at the point where you're specifying anything subjective, and all definitions in mathematics are subjective in that sense. But it reduces the surface area of things you need to check.
Yeah, you now need to only check the theorem statements and definitions. I don't need to check the proof, because lean does that job for
me. You also have to know a little bit of lean, because, okay, so one of the easiest ways to prove Fermat's last theorem is Well, you abuse this thing called natural number subtraction. So in Lean, natural numbers start at 0. So what a lot of theorem provers, Lean, Proc, Isabel, everybody, they all do this, is for the sake of engineering convenience, they say that subtracting a larger number from a smaller number always gives you 0, because this is a subtraction operation defined on these the natural numbers. The output is a natural number, right? There's integer subtraction, that's separate. But you can always write x to the power n plus y to the power n minus z to the power n equals 0, and then get these absurd proofs. And that's just the big tip of the iceberg. So you need to actually know what's happening in Lean. You need to know your definitions. You need to know the library. And this is why a proper standard formalized library is helpful, so that lots of people know what's going on in the library and they can spot this nonsense from a mile away.
More questions? Okay. Anybody from Zoom wanted to ask any questions? Thanks. Please feel free to unmute yourself. Okay, I think that wraps up. Thank you very much once again for a wonderful talk and questions and answers being answered.
I'm happy to stick around if people want to ask questions after the.
If anybody wants to
formal
have a
talk.
one-to-one chat with him, he's offering to be online for a few more minutes. Provided there is no other lecture in the auditorium booked, yes. I think there is nobody wanting to have it. So thanks once again for spending the morning with us and giving us a wonderful lecture. And
Thank you.
have a good
Thanks
day.
for inviting me.
Yeah, thanks.
Thanks, Shreyas.
Thank you.